Okay, time for another video presentation. Today's topic is going to be angular momentum and other angular quantities, basically taking rotational motion a little bit further. We've been making the correlation between rotational motion and linear motion in the last segment, and we're going to continue doing that here. So before we get started on the topic at hand, how are you doing right now with college level preparation? I mean, that's a good question to be asking yourself, since the AP class is designed to give you college experience. So from time to time we should discuss that. If I were to say to you, could you open up your notes to your linear quantities and linear momentum, let's say in particular, or linear kinematics? Could you do that? Are they organized in that way? That's a good question to ask. And how are you organizing the problems that you solve? You should be keeping track of every problem that we solve, which has been many by now, and thinking about making sure that you can solve all of those problems. And also, as I've said from the beginning, be thinking of where those problems could be taken in a new direction or taken a little bit further. Okay, well those are good questions to ask yourself. Okay, so today's topic again, going back to the idea of talking about linear correlations to angular quantities. And we had finished off talking about the idea of the sum of the torques was equal to I. Do you remember? Could you find the notes on what I is equal to? Well, it's the moment of inertia, and this is the angular acceleration. So torque is equal to the moment of inertia multiplied by the angular acceleration. And we had also discussed that the linear equivalent to this was force is equal to mass multiplied by acceleration. So that gets us right in the ballpark there. The other thing we talked about last time, so this is all review now, is that on the AP exam, the formula is put into this format, which is really just juggling this stuff around over here. But there you go. So they put it in terms of the angular acceleration. Okay. So a little bit more about the moment of inertia. Now we're talking about things that are rotating, and we're finding out that the radius is very dependent on the radius. So now let's think of a solid object, or maybe even an object that is not uniform at all. But now, instead of just one piece of mass and one radius, there's all pieces in there that have individual radiuses, radii, I don't know, is that a word? But at any rate, there's lots of radiuses and lots of little particles to consider when coming up with the moment of inertia. Now the linear equivalent is mass, but it's really about the distribution of mass. Okay, so let's see what else we could say. For a particle, it turns out the moment of inertia is its mass multiplied by its radius squared. And this will take into account all of the particles. Now, this is something, that we kind of have to take on face value here for now, the idea of the moment of inertia. We can talk more about it later, but we're going to be using this idea for a particle moment of inertia in some of the problems that we're doing. Okay, and here's another thing. If the moment of inertia is mr squared for a particle, then for a ring here, you can see now, a stipulation that has to be uniform, so the material has to be the same all the way through. But you could think of it as a bunch of different particles around the curve. And these bunch of different particles all added up together would give you the moment of inertia, which it turns out will be right back to what it would be for a particle. And you can think about the center of mass here as being right in the middle. Okay, so it's the same for a uniform ring as well. Here are a few other ones that are commonly used. They're good to know for our problems. So in particular, with these different moments of inertia for different objects here, in the upcoming assignment we're going to be working on two of them, and that's the solid cylindrical disc, where the moment of inertia is 1/2 mr squared. And also we're going to be looking at a rod that is rotating about the center. And there the moment of inertia is 1/2 the mass multiplied by the length squared of the rod. So there's a little bit of a close-up again on these two that we're going to be focusing on. It's good to be aware of all of them, but These are the ones that we're going to be using on the upcoming problems. Okay, so now that we have talked a little bit more about moment of inertia, let's talk about how it affects some other quantities that are related to linear quantities. So rotational kinetic energy, remember moment of inertia, the I is the rotational equivalent of mass in the equations, and here is the angular speed, and over here I've put the formula that we were familiar with, so you can see the correlation there from the rotational value and the linear value over here. Okay, and these energy concepts work into some problems that we'll be doing, not on the next assignment that you're going to see, but certainly on some problems that you'll see pretty soon. Along those lines, talking about this idea of energy here, we could talk now about including the rotational value into our idea of the conservation of mechanical energy. So all of the initial kinetic energy, translational and also angular, plus any potential energies I have at the beginning will equal to what I have at the end. And that should make some sense. Now this has to mean that it's all conservative forces. Energy will be dissipated if there's non-conservative forces at play. So we can talk about that as well. And here is the delta. It's really more probably familiar at the lower value over here to show you that the work of the non-conservative forces, of course, we took into account that it would change the kinetic energy and also the potential energy as far as mechanical energy, and now we're throwing in the rotational kinetic energy as well. It's a lot to take in, but in some ways it's a nice review because every topic that we've talked about with linear values that we built up during the entire year is now combined into rotational motion. So it's also a good time to review what we were doing earlier. And some of the problems combine both of these things. So it becomes challenging and it can be confusing. So bring your questions to class, please. All right, let's continue here with the idea of the angular momentum. And this is going to be the next assignment that you work on in class. So the angular momentum, and this should make some sense here, since in linear values, linear momentum is the mass multiplied by the speed. So it's probably not surprising at this point that the angular momentum is the moment of inertia multiplied by the angular speed. And we had also developed a concept of impulse. And the idea of impulse here, and this is a AP formula equation as well, is that the change in the momentum is going to be equal to the force multiplied by the change in time. So the angular equivalent here is that the change in the linear momentum, right, and that's the value here, L for linear momentum, is going to be equal to what? Well, let's see. Do you remember what the force equivalent was in rotational motion, angular motion? If you said torque, you are right on the money. So here, the change in, and again, L is the angular momentum, is equal to the torque times the change in time. All right, so that's the idea. We also spent a bit of time developing the idea of the conservation of linear momentum. And with angular momentum, there's also a conservation. If you don't have a net torque, so if the net torque is equal to 0, well, remember, if the net force is equal to 0, we have no change in momentum. So if there's no outside torque acting, the angular momentum stays the same. And that means that the initial angular momentum, remember L is the value for angular momentum, is equal to the final value. And that is it for today's short video. And again, bring any questions you have back to class, and we'll work on some problems with these new concepts. Thanks for watching.